Welcome back to part 4 of our series, where this week we're going to learn how to address the ROM that we created in the last video and how to scale the timer down to 1-second intervals. So let's jump straight in. In the last video we made the ROM, the character ROM, so that'll be in the notes if you need to jump back and review that one. Now we're going to make the address counter, which will basically count from 0 to 9 and do that every 1 second based on the 115 megahertz system clock. So the code today is broken up into two major parts. We've got the sysclock timing, which is what will do our 1 second timing, and then I have my address counting, which will count my 0 to 9 to clock my address, and then just the initialization. As far as my inputs outputs, I'm using my system clock again to do my clocking as we did previously in the 20 megahertz counter. So it's actually very similar code that we'll be using here. For demo purposes, I've outputted my 1 second clock. Then I've got my address, which is a 4-bit address for the 1 to 9, and a temporary account, which again is for demo purposes. So we'll delete that once we get to the proper code. Basically what I'm doing is I'm counting up to 126 with however many zeros that is. I've just capped it down so it's quicker for compiling and testing, where my address should count up to, and a couple of variables to go through with that. So looking initially at the counting, so I've broken it up this time into a couple of different detections, and this basically forces the synthesizer to more concisely create what I want. So this part will create me a flip-flop, and this part will create me a counter, whereas when I combine them together, the output may be a little bit more jumbled. So this helps just keep it a little bit cleaner by, if you think of this as a discrete piece of electronics, it will separate the electronics. So looking initially at the counter, all we're doing is a comparison that if count, which we've set to be 0 initially, matches my constant number, the 126 at the moment, take 1 because we don't want it to go over, then we'll reset the count back to 0. Otherwise we'll just increment the count until we get to that point, and we'll keep on doing this. Now when we're running these two always, even though they're separate commands, they actually happen at exactly the same time in code. So the moment that we get this high clock pulse, both of these lines of code will actually execute at exactly the same time. We're doing a comparison of if we've hit the constant number, which means we've hit 1 second, we'll toggle the state of the bit that will be for our 1 second pulse. If not, we'll just make the state the same as it was before. So this is basically a safety clause. We could pretty much eliminate it, but it's just a safety thing that there's always a state locked in. So basically this is doing all the work. It's just toggling every time we hit that counter value. And the last part is, if it hasn't reached the maximum, we're just going to increment the count until it does get to the maximum. And that count will then be outputted at address current. We'll see up here, address is equal to address current, and that will put it into there. Now I could have done exactly the same as I've done here, is put a reg before it. I just thought I'd use the 2 to show you. So if we define an output with a reg, that means that we can directly write to it like we've been doing down here. Whereas if we don't specify the reg, we need to do an assign. I'm not really sure if there's a real advantage of one over the other. Maybe someone, if they know, can put that in the comments for me. In the waveform, we can see the address and the incoming system clock, and the other two are just for reference only. So this is my 1 second clock, and if I click on there, you'll see it's happened at 10 nanoseconds. So if I had all those extra zeros on my count value, that would be the 1 second. But just to make it easier to demo, we've changed it down. So every high going edge, we're counting up another cycle. Interestingly there. All right, so I've just noticed that I hadn't looked at my code well enough, and my 10 nanoseconds is occurring on the low going pulse instead of the next high, which is, so we're going up slightly higher than what we want, but basically what that tells me is if I go back to my count, this value down here should be half. So if I halve that value, they would be, apart from that very first count, which would clean up after one cycle, it would be exact. So let's go back into the code, into the timing. So we can see, ignoring that error, that every time we're counting up until we get to 9, and then we're going back to 0 again. And you'll see this 0 is the full length as opposed to the first one. So it's only that power up. Ideally, we should have a reset command during power up. All right, let's zoom in a bit. So there, if you were to count the cycles, you'd find there's 126 of them. And in here, we've got the 7D, 7C. So this is the actual count that's going on. So hopefully that step there was clear for you. It's fairly much a repeat of what we've done in the past. But if you've got any questions, throw them in the comments. I'll be more than happy to either answer in the comment or do another video. In the next, we're going to be also sharing that address with the color select that will decide based on what the count is up to as to what color to output. That will give us, I've said here it's an 8-bit, but it'll actually be a 24-bit number. So it'll be in this format down the bottom. That will go through to the color mix. Now, this is actually really simple code. So again, it will be a quick video. I should have that out in a week. Hopefully you're getting something out of this. If you are, please give me a thin thumbs up. And I'd love to hear from you if you've got any suggestions of other content you'd like me to cover. Catch you next time.